Hi everyone. So we're going to talk about how to sort these reactions. So I gave you this list of reactions the other day, and if you've not had a chance to look at it and flip through it, I encourage you to go do that and then come back here and watch how I'm going to sort them. So we start off with this list of reactions, and at first glance, you feel a bit of panic. I mean, it's a long list, and there's a whole bunch of stuff going on, and it just feels like there's stuff everywhere, and there's no rhyme or reason why we should put any particular reaction together. So we cut them apart, and we start to take a good look at them, and what goes in, and what comes out, and how that's going to work. And one of the first things that kids will typically pull out and identify are these sets right here. See, this set, I take two things and I end up with one thing, or I might actually end up, I don't think any of these do it, but sometimes we'll put three things in and we'll end up with one single product. Okay, the word for that, what we're going to call those is synthesis. So again, I'll put those back. Our synthesis reactions to, okay, like that. Okay, again, all start with two or maybe more products, two or maybe more reactants, and then make one product. So we're going to write that down. Two or more reactants make one single product. Oops. Okay. The next thing then, some of these you'll find, dig through a little bit, and you'll get 20 and 4 and 7, and you'll find, got a little ahead of myself, that some of them are just the opposite. Start with one reactant, and we end up with two or more products. Call it a decomposition, right? To decompose means to like unmake something, okay? So again, basic, what happens is one reactant makes two or more products. Those parentheses there. Okay. So then we kind of look at the rest, and we're in a little bit of panic for a second. And then we come across, say, these right here. Well, these sure look almost identical. Everything in these things seems to be almost the same. The only thing that differs a little bit is the numbers. And whether or not, oopsies, kind of lost that one guy there. Some of them have O's in this initial compound, but everything else appears to be the same. Well, we talked about anytime in a reaction, when you see plus O2, not every time, but often in a reaction when you see plus O2, what it means is that this is burning. So we call these reactions, turn my page, combustion. Now, combustion doesn't mean to explode. Sorry. Combustion means to burn. So we're going to take these compounds, composed carbon and hydrogen and sometimes oxygen, and we're going to burn them in air. And you'll notice that the products of these reactions are exactly the same thing every single time, that we always get water and carbon dioxide. So this is a CHO compound, for lack of a better term right now. Burns in air. To produce water and carbon dioxide. Okay? So the last of the reactions, that's where we get a little bit intimidated, and everything seems to just kind of all smoosh together. So I'm going to go ahead and pull some sets out for you. Pull this set out first. Well, what this set has different from most of the others is that I start off with a compound, and you'll notice they're always ionic compounds, and some element, like calcium, even fluorine is a diatomic element, but it's still an element, right? And magnesium, and then what I get out of them is, again, another different compound, and an element, and a different compound here, and an element, and so on. So what happens in these reactions is this metal right here displaces this metal right here and kicks it out. So this calcium comes over and steals aluminum's place and ends up stuck to the nitrate. And the aluminum is now sitting all by itself. Isn't it sad? So the calcium is bigger and stronger, and it beats up the aluminum and kicks it out. And the same thing goes for the fluorine, kicking the bromine out, and the magnesium kicking the copper out. Now, why does the calcium kick out the aluminum and where the fluorine kicks out the bromine? Well, remember that calcium is a metal, and the metal ion, the positive ion, is going to have to kick the positive ion out of the compound, and then this non-metal ion, like fluorine, has to kick the non-metal ion out of the compound. So we call them single displacement because we have one thing that gets displaced. We say an element and a compound react to form a different element and a different compound. Oops. Okay. And then we have the rest of the reactions. And, well, we're going to have two more groups. I want to look at them all together. So these reactions that I have left all look very, very similar. Notice that every single one of them takes two compounds and makes two compounds, right? So, but this seems like a really big group. Like I should divide this into smaller pieces. So how can I do that? Well, as I glance through them and I look at what they have in common, we'll notice that like this reaction and this one and this one and this one all end up with water as one of their products. Well, why is that? We'll set them. Whoops. Set aside the wrong ones. Okay. Why is that? Why do they do that? Well, they all start off with these very specific, very similar beginnings. I start off with a compound that starts with an H, and then a compound that starts with an OH. Now, those of you who have learned how to name these things, some of you will recognize these compounds that start with H's as being acids. And what you haven't been told before, what we've not discussed, is that these compounds that end in OH's, yeah, they're bases. So what these are acid-base reactions. I'll bring that out in a second. But I start with an acid, that's a compound that starts with an H, and a base, it's a compound that has a hydroxide ion, and I get an ionic compound made out of this ion and that ion, and then water, which I'll show you in a second what that water is. We'll write those in a minute. We'll talk about these first. These reactions now just look like a hot mess, and there's stuff happening all over the place. But basically the same thing happens. I take this ion plus that ion. I take the sodium plus this chlorine, and I stick them together. And I take this calcium plus this carbonate, and I put them together. Now, we're asking what happened to this 2? Well, remember that in this ionic compound, this 2 right here on the sodium is not from the sodium. It's the charge that came off this carbonate right here. So there was a 2 and it crossed down here, and there was a 2 in the calcium that crossed down to this chlorine. So sodium only has a +1 charge, so it would only take 1 chlorine, right? And they cross down there. So I start with 1 ionic compound, 2 ionic compounds. Notice that they're both aqueous. Typically, ionic compounds don't react when they're in their solid form unless we're going to like heat them up and decompose them or something. And I get this sodium chloride, right? That's also aqueous. And then I get this one right here that's going to be a solid. Now, those of you who've done this reaction with me will recognize that when I put 2 ionic compounds together and I get a solid that comes out of it, this is a precipitate. We've seen a lot of these reactions. Okay, let's bring those back. Sorry about that. All right. So, that most recent type, those are called, what did I lose them? This right here, these are called double displacement reactions. And I take 2 ionic compounds react to form 2 different ionic compounds. Well, back to our acid-base ones for a second. I pulled them out a little quicker than I wanted to. You can see they really are just double displacement reactions. There's a fancy version of a double displacement reaction. See, I still have, well, this isn't quite an ionic compound. It kind of thinks it is. And then this ionic compound, and I get 1 here. But water's not an ionic compound, you say. Well, if we treat, oops, I'll draw that a little higher, this like it's an H plus ion, also, we take this HCl and the CaOH, well, we end up with this calcium hydroxide, and then we end up with the H and the OH stuck to each other, right? And while this looks like an ionic compound, sort of, if hydrogen was a metal, if we rearrange it, because it's not really an ionic compound, we get this 2 H's and an O. So, an acid-base reaction, a hydrogen compound reacts with a hydroxide compound to produce an ionic compound and water. Again, it's just that HOH. There you have it. Those are your reaction types. Thank you all for listening.